So here's a quick lowdown on the topic of vectors. We talked about it in class before, but we know that a vector quantity is something that has both magnitude and direction, right? So we can represent a vector using an arrow. The direction that the arrow is pointing is obviously the direction of the vector, and the length of the arrow, the length, represents the magnitude. So here's some examples of different types of vectors that we've talked about. Displacement is one, velocity is one, force is one we'll get to later in the class. Now, a scalar is just a similar idea, but it only has the magnitude. So it's really nothing to do with direction, right? It only has magnitude. And so some of the ones you've seen before, distance, speed, mass, we haven't talked too much about that yet, but we will. But so for example, if someone starts here and walks here, start, end, then you can say the length of this, the distance they walk along, if you just talk about the distance they walk, that's a scalar. But if you talk about the distance they walk plus the direction, then the two of them together is a vector. So how do we add vectors? So if you've got multiple displacements, for example, or multiple velocities, we do it using something called the tip-to-tail method. And the tip-to-tail method involves placing the tail of the second vector. So this is the tail of the second vector, and you attach it to the tail of second, to the tip of first, right? So you can add multiple vectors that way. And when you get to the end, the solution is going to be, for the answer, for the total, is from the tail of the first. So this is the tail of first to the tip of last. So let me just go through that again. When you're actually, let's say you're walking and you actually walk this displacement right here. So you do that, and then you do this, right? So those are the two displacements you have. So it's just like taking arrows and laying them tail of the second to the tip of the first, but then you can see that when you put it all together, the actual final displacement is going to be from the tail of the first to the tip of the last. So that's an important concept. We're going to use that a lot. So you see we're forming these triangles, and those triangles are going to become the basis for how we add vectors. Let's see. So you have to think about direction. Direction really matters. So it says when adding vectors, the direction will determine the magnitude of the resultant vector. So you can have two vectors. Let's say they're each unit, 1 unit. I don't know, 1 kilometer, 1 meter, whatever. So here's a vector that's 1 unit. If I have two vectors and I'm adding them together and they're both in the same direction, then the resultant is going to be twice, right? So this is going to have 2 units. Let's just say kilometers. So if the first one is 1 kilometer, the second one is 1 kilometer, then your total displacement will be 2 kilometers. But what if this situation happens? You walk 1 kilometer this way, and then you walk 1 kilometer back. 1 kilometer. So now your total displacement is 0, right? Delta D equals 0 because you ended up where you started. So that's another scenario. Here's a third scenario. So you have a situation where you have the 1 kilometer like this, and then a 1 kilometer like this. I'm not doing a very good job of this. Let's say it's like this, 1 kilometer. And so the resultant is from the tail of the first to the tip of the last, so it's going to be this. It's also 1 kilometer, if I get my angles right. I'm assuming I've made this 60 degrees and 60 degrees. So we've got an equilateral triangle. So you can see there's 3 different scenarios here. In the first scenario, 1 plus 1 equals 2. In the second scenario, 1 plus 1 equals 0. And in the third scenario, 1 plus 1 equals 1. So all are possible. So what I'm really trying to say here is direction matters. Direction matters. You can't just add numbers, right? You have to draw the triangle. You have to lay it out and map it out like that. And the order doesn't matter. So that's something you can keep in mind. When you subtract vectors, it's exactly the same idea. What we just do instead is add the opposite. So let's say you want to do this, a minus b to get d. So if this is b, so these are the same 2 vectors I'm looking at from before. Instead of adding them, I want to subtract them. All I'm going to do is take the vector b and reverse it. So and the opposite, the negative of b, so you must find the negative of the second vector. That means opposite direction. All right, so then it's the same idea. You add them tip to tail. Tip of the first, A is the first, so the tip of the first to the tail of the second, and then your resultant goes from the tail of A to the tip of B. So that would be D, which is A plus negative B. All right, looking at components of a vector. A component is a really useful tool, okay? And it's along a frame of reference, which means the components are always perpendicular. Are perpendicular to each other. Okay, so what that means is when we make triangles out of components, they're always right angle triangles, which is a very useful tool. You'll see the more we do, the more you'll see why this is a useful tool. But a right angle triangle like this can be easily solved using SOHCAHTOA. So we have a few tools. SOHCAHTOA, SOHCAHTOA. We can use Pythagoras. I think that's how you spell Pythagoras. So those 2 things are going to help us solve this triangle. And so what we're interested in here is if you know, let's say you know v, the final vector, and you know the angle. How do you find so like this, the first thing we'll do is find the components. Find components. And I'll put this with the blue so that you know it's like the same idea. It's the same, so I'm finding components if I know the actual vector and the angle. So in order to do that, all you have to do is use Pythagoras. So not Pythagoras, you would use, for the x-axis, you can see that Vx is the adjacent. So you can use this principle. Cosine of theta equals opposite over adjacent. So then we can say cos theta equals, now the opposite, sorry, I did that wrong. This is hypotenuse over, and the hypotenuse is Vx, and the adjacent, I did this all wrong. Sorry. Let me redo this. So rewind. I can't rewind. I'm just recording. So if I want to find the x component, so I'm interested in looking at this, the x component of V, I can see this is the adjacent side of the triangle. Adjacent. This one is the opposite, and this one is the hypotenuse, right? So what I'm actually saying is cos theta equals adjacent ADJ over hypotenuse. All right, so then what we can say is cos theta equals, the adjacent sign is just Vx, and the hypotenuse is just the actual vector V. So if I want to solve for Vx, it's just V cos theta. I'm not going to go through the whole thing to find the others, but you can go through a similar math to see that Vy is equal to V sine theta. And this is because I've solved the triangle, okay? This isn't like you always know it's to be true. Given this triangle, these are the answers. Now, what if I know the components and I want to solve for the actual vector? So I would say, so let's say I know this and I know this. Well, if I know those two things, I want to find the vector. Now I want to find, I want to find the vector. Find the vector. And I mean magnitude and direction. Now is when I can use Pythagoras. So in order to find the vector, I'm going to use Pythagoras. So V equals the square root of Vx squared plus Vy squared. And I can also use the relationship that tan theta equals opposite over adjacent. That's the ta in SOHCAHTOA. So then tan theta, so then what we can say is theta equals the tan inverse of Vy over Vx. All right, so then that is how you would find those two things. So these two formulas, and they're written on the sheet, but that's how you got them, okay? I'm gonna stop there and we'll do examples in a